Okay. Well, good evening, everybody, and welcome to the May Mixer. We have a couple. I know Eric won't be attending tonight. Michael's away as well, and I think that covers off. Ken, I see you're here. That's good. Tonight, reminder that our meetings are recorded and are made available on our for the public viewing on our YouTube channel. So we get that out of the way. Tonight on the agenda, we have Dave OI going to talk about his solar tracker. I just wanted to spend a couple of minutes to talk about the solder rework stations as well. That shouldn't take too long. I want to bring up date in 4 days of May, and maybe Hassan might want to talk just a little bit on the 4 days of May challenge. Now, speaking of Dayton, the meeting on the 15th, for those, there's going to be about, I guess, the regular participants in this meeting, there's probably going to be about 6 of us that are going to Dayton. So I think last year, I think you had the meeting, you had a casual gathering of everybody that was kind of left behind, for lack of a better way to put it. So I don't know what you guys want to do, whether you're just going to meet on the 15th or just outright cancel it. So maybe we can do something, talk about it a little bit here, or I can always decide, I guess, via Yahoo, or not Yahoo, Groups.io, whether you want to have a casual meeting. Who knows? Maybe when we're at the bar hotel, we can sign in, because I think we did that last year, and we just sort of checked in and just kind of said hello and showed the bar and all that kind of good stuff. So I guess we'll leave it open. But anybody have any comment on whether you want to just forgo it, or are you going to meet for a casual meeting, or what?
Hey, Peter, could you also start recording as a backup in case mine fails?
Oh,
because at least that way we've got.
Just bear with me for a minute here, guys. Okay, I think I'm recording. As far as I know, I'm recording. Oh, yeah, there we are. Let me just turn off my camera here. Okay, where were we? Okay, I guess so. If you want to, I guess we'll just let it play out on Groups.io. If you want to, if a bunch of you want to get together on the 15th, and maybe what we'll do when we're at the 4 days of May hotel, maybe we'll do a quick sign in on Groups.io, and just to see if there's anybody there, and to say hello and introduce around the table, whatever we got going on. Let's see what else we got going on here. Okay, I guess, Dave, are you ready anytime for your presentation? Yeah, okay, well then, I guess get started whenever you're ready.
Sure.
And then after you finish that, then we can do that, the topic of interest I wanted to talk about, and then we'll talk to Hassan a little bit about the 4 days of May challenge and the roundtable. Okay, Dave.
So there, can you guys see my screen?
Yeah.
Okay, so this is a presentation. This is a continuation of the presentation I did a couple weeks ago on some of the things I did during the solar eclipse. And last presentation I did, I talked about my QRRS beacon and some of the data I got back from reverse beacon, and some of the interesting results. I got back. In this presentation, I'd like to continue on that and talk about something I call the solar tracker. And basically what it was, it's something I used to track the sun during the eclipse and make measurements of various aspects of the sun, of aspects of sunlight. So here's the agenda. So I need to talk about the background and the configuration. And I've got about a total of about 40 slides, and majority of it is around the architecture, because you really need to understand that. Otherwise, the data will make no sense to you. So you really need to understand what I'm doing, why I'm doing it. And then once you see the data, it'll make sense. So as always, take what I say with a grain of salt. Old physics guy who hasn't done this stuff in years and years and years, and some of it's a little bit rusty, so I may say things that are not completely right, but so take things with a grain of salt. And as with my other presentation, this came about from last year at Hamvention. HamSci talked about what they're planning to do during the eclipse, and that just planted the seed in my head to say, hey, you know what, this is a good opportunity for me to do some experimentation. I showed this slide before, and it just gives you a sense of the timeline I worked with, because I started this back in December of 2023, and I worked on the beacon. That's about 4 months before the eclipse, and I worked with my beacon for about 3 months, and then a month before the eclipse, I got this. I don't know what inspired me or how my mind works, but a month before the eclipse, I decided to go and build this tracker. And so in that month, I had to go and do all my CAD drawings, 3D prints. None of this stuff is stuff which I pulled off of the internet. It's all custom stuff. Everything I did was, so I had to build the CAD drawings myself, 3D print. I had to do the milling, the PCB prototypes, milling, everything I had to do. I used 3 processors here. I used an STM32, which I had to figure out, go back and figure out how to do programming and what the I/O structure and the timers and all that kind of stuff. So I had to figure that out, because that did servo control, that did the data collection, it did the synchronization, and communication. It was like the brains. Then I had 2 ESP32 with camera modules. So I had to go back, figure out how they work, and they were a pain in the ass to figure out how to work, because there's a whole bunch of problems, challenges with these things, which nobody talks about. So I had to figure those things out on my own and work around it. But basically I use those for the camera, and it's got an SD slot. So I use that to store the data. A lot of it I used I2C communication. I had to figure that out. Then I had to figure out ESP now, and I'll explain why I had to do that. Then I had to build a pinhole camera. So all this stuff I had to do in a month. And so what happens when you try and do too much in too little time? Well, Murphy comes, pays you a visit, and you end up, putting the cart before the horse, and things go wrong. And so in light of this, I created something called my Murphy's log. And I talked about that before. And basically in that log, I'll show you what worked, what didn't work, what some challenges were. So I keep track of it as I go through my presentation. So let's get into the architecture of the solar tracker. Now I realize that I can put this into full screen mode and show it like this, but I like doing this because I like to jump around, and because I know what slides are coming up. So one of the first things I had to do was figure out, okay, what am I going to measure here? In the beacon project, this is the spectrum here, electromagnetic spectrum, going all the way from gamma rays to radio waves. And before, when I was at school, in grad school, a lot of my work was in gamma rays. That's where I did a lot of study. But so I had to decide what to go and measure. And so as part of the Beacon project, I measured radio waves and propagation, so that part of the spectrum got covered off. So I decided to, I would measure ultraviolet light, visible light, and infrared light. So that was the three goals: to measure that type of radiation coming off of the sun. So here's a little video I'm going to play, and as I'm talking, you'll see this is an early prototype, and you'll see me moving the light here, and you'll see it tracking the light. So I had two large servos on hand, and I decided to use those for azimuth and elevation control. And you can see one of the servos there, and that's a servo controlling elevation. There's another servo here mounted below this, and that's doing the azimuth, going left to right. And as well, I had create this tracking jig. Now, this was all over the internet. A lot of people use this jig. So I just borrowed that from other people who use that to build solar trackers. And on that, I mounted, you could see the little black dots there. Those are infrared diodes. And also I had photoresistor sensors. So each quadrant here has got a pair of sensors, and that's allowed me to do the tracking, as well collect data. As with any project, you got to throw in a solar cell. It's the solar cell was not used to power this, because I'm sure someone's going to ask that. Did you think about using the solar cell to power this? No, it's a sensor. I use it as a sensor. It just doesn't generate enough current to drive servos. So it's being acting as a sensor. Then I had an ambient light and an ultraviolet light sensor. They were both I2C devices, and you could see them here. I've got a better picture where I'll zoom in. I'll show you all the sensors. Then what's not shown here is the ESP32 camera modules. In a subsequent slide, I'll show that. But I had one mounted to the face of this, which will be taking pictures of the sun, and it's got a solar filter attached to it. So that would be one device to taking pictures. Then I decided, a week or 2 weeks before the eclipse, I decided I'm going to do a pinhole camera. So I had to just bring this ESP32 cam module for the pinhole camera, and I'll explain why I did that and what happened there. But I used another ESP32 cam module for my pinhole camera. Then I had a temperature sensor, which is not shown on here, which you'll see in a subsequent slide. And I mounted a metal plate to it, and I thought I could use that to measure the thermal flux coming off of the sun. And that's just the heat. How much heat is delivered per square inch of a surface. And I had a main STM32, which is this board here. And that's the brains of the whole thing. So that's measuring, capturing data, it's tracking the sun, and it's syncing up data with the ESP32s. So here's the concept of my thermal flux. And this is important. This is why I said, you have to understand the architecture, because when you see the data for this, it'll make sense. So what basically, I've got a temperature sensor, and I've got a plate in the shape of an L bracket attached to it. And this is the side view, and here's the top view, and here's the temperature sensor. So the idea is the sun shines on this plate, heats it up, and I can measure the heat that's on this plate via this, and I can measure the flux. So I'm measuring how much thermal energy is delivered to this surface as a function of per square inch. And I could track that as a function of time as the eclipse goes on. So that's, in theory, what I want to do. Here's the actual equipment. This is the actual final setup here. You can see, here's the ESP32 module here. You can see the solar filter. It's attached with masking tape. Real high-tech engineering here. You can see the thermal sensor here. I got a better picture, much close-up, where you can see the sensors. There's the IR camera, the ultraviolet ambient light sensor, solar cell, and you can see the IR diodes there. The jig, there's the battery controlling it. It's a LiPo battery, and I had to put a little display showing the voltage, because you don't want to discharge your LiPo beyond a certain point, because you'll damage it. I built also a jig to mount a cell phone camera so I could take pictures. I didn't have a good camera, nor did I want to use a good camera because I was afraid that I might damage it. So here's the pinhole camera, and I've got another slide which I'll show what that's doing. So here's some miscellaneous thing. Here's a video. So this is the 3D print of the turntable, which gets mounted to this base plate. You can see the servo there, and you can see the plate, the attachment plate there. You can see a hole in the middle there. That gets attached to that plate, and this servo rotates it to get the azimuth. And this is just a board, the prototype board that I used to control it. This is what the STM32. You can see the footprint for the STM32. All my sensors connected in here. Up here was I2C, servos attached up here, and voltage input regulation here. I had to put 2 voltage regulators. I had to have a 3.3 volt regulator and a 5 volt regulator. The 5 volt regulator needed a huge heat sink. Not well, not huge, but it needed heat sink because the current draw from these servos got this sucker to get quite toasty warm. Not warm, hot, where you could burn your fingers on it. So here's a zoomed in picture of all the sensors. You can see the thermal flux sensor here. So that's the metal plate. And I jerry-rigged a little PCB board here to attach the temperature sensor to it. And so the idea is to measure the thermal flux, striking that plate. Here's the IR camera. Here's the UV and ambient light sensor, solar cell. And here you could see the 4 IR diodes. And they just basically, as more IR light shines on them, they allow more current to flow through. Same thing with the photoresistors. It's a photoresistor. As light shines on it, the resistance drops, and therefore more current flows through it. Here's the ESP32. It's a W Rover module, which has a camera built in. And below this, it's not shown, you can't see it, but underside of this, it's got the SD card that I use to store the data from the STM32 and to store the pictures that the camera would take. Here's a side view of it showing the sensors, but here you can see the servo. So this servo is controlling the elevation. It's swinging this up and down, and below this turntable is not properly attached, so you can see it hanging off. It just, for the picture, I just kind of put it on the top to get the picture, but there's a servo mounted at the bottom that attaches to this round turntable, and that causes it to rotate left to right, the azimuth. So for the pinhole, what I wanted to do was, if you took a set of pinholes and you projected it onto a screen during the eclipse, what would happen is that during the eclipse, these little circles you would see, lighted circles, they would become half circles or quarter circles as the eclipse progressed. So I thought, okay, you know what? I'm going to attach that to the side of my tracker, and I'll be able to capture that. Well, that didn't work out very well because, number one, I had issues with the focal length of the actual image and the ESP32 cam. They had different focal lengths, and I had issues with that. But the biggest issue was the weight. Now, some of you may have caught this, but if you look at the axis of rotation, it's going through here. There's a servo, and the axis of rotation is there. So it's rotating about this point. Well, you've got all this weight at the top here. And before, I had this board mounted to the actual top at one point. And this thing was just drawing an immense amount of current, and I couldn't understand why, until one day it just dawned on me. I created a hammer. Basically, all the weight up at the top, and you're swinging this hammer. So the amount of inertia you're swinging is huge. And as well, if this gets, it goes down and it's, pretty much horizontal, gravity's pulling all that weight down, and it's a huge moment. And this poor servo is just sucking back current. Sometimes it pull 1.5 amps of current. It'd be pulling, and my poor little LM, what's it, 7805. I think they're rated for like 1 amp or 2 amps. It was getting hot. I could fry an egg on it. And the other thing was the wires. These wires, you'll notice the wires are mounted at the axis of rotation before they were mounted below, and it was acting as a spring, and it would impede the motion. So there are lots of issues around this, and so this is why I decided to do a separate pinhole camera, because I just couldn't do this here. So my Murphy's log, I have two things. One is, to reduce the moment arm of the tracker. Next time, use a stepper motor instead of servos. Servos just can't do this. Stepper motors would probably be far more efficient at doing this. And I don't know what possessed me to use Cat5 wiring for this, because it's solid wire and it's basically a spring. I should have used, I don't know why I didn't use softer wires, but hey, live and learn, right? So here's the concept of the pinhole camera. So as I said, there are two focal lengths, and what I had to do was put a screen between the pinhole. So the pinhole's here, so the light gets projected from the pinhole, gets focused on this screen. It's a translucent screen, and then put the camera at the back of it to take pictures of that translucent screen, because the focal lengths were quite different, because at first I wanted to mount the camera at the pinhole, but the focal lengths are different and it just wasn't working. So you could see that the pinhole camera broken apart. Here's the translucent screen, which fits inside this box. And then on top of this, I have a card that gets taped it, and that's got the pinholes. So this goes inside, and you can see it sticking out here. You could kind of see this side of it sticking out there, and that's the pinholes there. And inside at the bottom, I've got my ESP-CAM32 module. Now, originally I wanted this to be connected I2C back to the STM32, and what I found out was this ESP32 CAM modules, if you're using the SD card and the camera, there are no free I/O pins. You can't use I/O pins. And I spent days trying to figure out why I2C was not working with this device. And it turned out what the pins didn't allow it. I couldn't use it. So I couldn't use I2C. So hence I had to use this protocol called ESP Now. And it's a proprietary expressive protocol that runs over Wi-Fi. And so I use that to communicate between the two ESP32 modules. So to add to my Murphy's log, ESP boards, if you're using them, make sure you know that they've got free I/O pins. So here's kind of the logical architecture of what I did of the tracker itself. So I've got my STM32, which is the brains, got all my analog sensors. These are the photoresistors, the IR diodes. They were all the STM32 is measuring voltages from those devices. Then I had some digital sensors, which are I2C connected. They were the ultraviolet and ambient light, the IR camera. That was all connected through I2C. Now, with the IR camera, what I found out painfully was that it's taking a picture. And so I've got to pull all that data, and it's like 3 or 4K kilobytes of data you've got to pull across I2C. Pulling it across wasn't a problem. Okay, transmitting that to the storage device was a problem, because there's something called the Arduino HAL, the hardware abstraction layer. And whenever you program anything using Arduino Arduino code, you're going through this Arduino HAL, and that HAL, I shake my head at it. It makes things easy for someone who doesn't know how to program a microcontroller. But once you want to get in and do, more meat and potatoes, it blocks you from doing it. The Arduino HAL, the buffers are too small for transmitting data. Now, I could have sent 100 bytes at a time, sent it, and then 30 seconds later another 100 bytes and so forth. The problem is I wanted this to be in real time. I want to take a picture, transmit it, take another picture, transmit it, take another picture, transmit it, and I couldn't do that. So I ended up having to ditch the IR camera because I just couldn't do it with this architecture. I could probably have worked around it, but I just didn't have enough time. By the way, can you guys still hear me? Am I still on?
Yeah, no problem, Dave.
Yeah.
Okay, good. So that's the digital sensor. So I had my ESP32 camera module, which has got an SD card. So via I2C, I would send it a signal to say, take a picture. Here's data, store it to the card. So this is the camera that had the shield, the filter, taking pictures. And then I had the pinhole camera connected to ESP now. That's a Wi-Fi protocol. So the STM32 would tell this camera, this module, take a picture, save data. Then this module will tell this module, take a picture, here's some data, back it up. So I had the data stored in two places. Call me paranoid. So next time, ditch the HAL. Use bit bang, I2C. And I've done this before, back when I used to build rocket flight management systems. That's what all my stuff I wrote completely at the metal. Here's a DSPIC, which doesn't have any libraries. There's no cool libraries to go use. You have to go and write everything from the ground up. And here I have an XB module, a GPS module, a IMU, and all this I use. So I could do this, I just didn't have the time to do it with this project. So what worked well was the analog sensors. I was able to get those working, store the data. The digital sensors worked well as long as the data was less than 128 bytes of data. I think the total amount of data I was saving was of the order of about 52 bytes or 50 bytes. So it wasn't a problem sending it across. So one of the things I did was this what I thought was clever. Here's the data I would send across. This is called a structure, and it's just you group a set of variables together. And I've got this thing called the header, and you can see it here. This is just what was stored on the SD card. It stores this thing called a header. It's the minute, so it says, I sent you a signal to take a picture. Here's my data at 1 minute, at 5 seconds. So this is just the start of the program. So I would note the time it was started. And from that time, I would add 1 minute, 5 seconds to know this was the data. And so I got, this is the data got stored. One of the things I did, which was in hindsight a really good thing, is I also stored the servos placement, the azimuth and position. And it was a good thing I stored this because this came in very handy. But the reason I did this header, and this header was nothing more than I just took these numbers and I shifted them to fit in a 16-bit variable, so an int. And what I did was I used this header, which is just this timestamp shifted, and I would timestamp the image. So when a camera takes an image, it would use that number. So when I sent this data, this line of data to the ESP32, I'd say, take a picture. It would take this number, take a picture and assign it. And the reason I did that, because what I wanted to do was say, okay, this line of data goes with that picture. So I could see what was going on. That, in theory, that's what I wanted to do. This is, by the way, this is the SD card listing. This is the directory listing of the SD card. So you could see the images being stored here and the numbers and the header values. So enough said, let's move on, then look at the results. So here's the setup. Here's the actual tracker. It's actually running here. It's live. It's tracking the eclipse. And I put it in a table. Here's the pinhole camera. And I put it at the front of the cottage we were at because we had a really clear view. And I didn't have to juggle it around. I could leave it here. Here's my Kona pickup truck. And just as I show you the data, I showed this before. Let's just make sure we're all on the same page when I talk about C1, C2, so forth. So in terms of the eclipse progressing, this is the eclipse progressing along in time. And as the moon touches the sun, that's called the first contact, or C1, contact 1. And where I was, that happened at 1:58 p.m. Then as the moon moves across the sun, once it ends, it completely covers the sun. It just kisses the end of the sun here. That's called the second contact, or contact 2, C2. And that happened at 3:13 p.m. In Leamington. And then at that point, you had a full eclipse for about 2.5 minutes. And the time that the moon moves off the sun and sunlight starts coming through, that's called the third contact. That's called C3. That happened at 3:16 p.m. And then the moon continues to move off. And once the moves completely off of the sun, that's contact C4. That happened at 4:28 p.m. So drum roll, here's the data. So here's the data from the IR sensor. So this is the infrared diode. This is from the light photoresistor and the solar cell. The red trace, so this, I've also showed the contact points. Here's C1, here's C2, C3, and here's C4. So the orange trace is the IR light coming in. The green trace is the solar cell voltage, and the blue trace is what the visible light that's coming from the photodiode. The data has been normalized to 100. That's why it looks so neat. These were not, I didn't get values of 100. I took the values and I normalized them to be 100 so you could see how they vary. So one thing to notice is right during the eclipse, everything drops out as you would expect. Hooray. So that was what we would expect, is that it would go dark and all of our sensors would go dark. However, if you notice, it's shifted a little bit. And I suspect what it is, that's my clock. Because I was using the STM32 timer to measure the time, the minutes and seconds, and I think that was off a little bit. So I think that's what's causing that problem there. But, notice everything drops at the same time, which is good. The other thing, notice the IR sensor here is less affected by the getting near to C2. It continues trugging along, and it doesn't start dropping off until well into C2, or closer to C2. Same thing with the solar cell, the green trace. It holds out, the drops further than the IR or the photoresistor sensor. So solar cell is definitely a good sensor to use to track the sun. Yeah, that's everything. So So the success sensor data worked really well. I was really pleased. I got some really good sensor data. It matched up with the cycles, C1, C2, C3. It matched up really well. I think something to improve is maybe use a real-time controller, an RTC to track what the real time is, so that I'll get better timing as opposed to using the Arduino clock, or the STM32 clock. So if we zoom in on this data, this is where it gets kind of interesting. If we zoom in right near the eclipse, we see some strange happenings here. So we see, again, the orange is the IR light. And by the way, the IR is what I use to track the sun. I use that to actually track the sun in the sky, because I found using the IR sensor, it was far more accurate in terms of tracking. But if you look at the IR data, it gets all gnarly. And that's a technical term, gnarly. It's getting all gnarly here, like it's getting gross looking here. But the other sensors are quite, looks quite smooth. So what the hell's going on there? And it's just before C2 and just after C3. What the heck's going on? So I kind of scratched my head, but I thought, okay, you know what? Let me overlay. I got the servo data. Let me overlay the servo movements to see what the servos were doing. And sure enough, you could see the servos moving right during this period. So during this period, I think what's happening, it was trying to acquire the sun. It was losing tracking of the sun, and it's trying to acquire it. So the PID I use to move the array, it wasn't very good. And so I got a lot of jitter, a lot of noise, and you could see it as well here. It's trying to pick it up. Now, the interesting thing is, I did notice, I would periodically go and look at the tracker. Just after the eclipse, I went to it to make sure it was still working, and I did notice it was moving around a little bit. And it was trying to lock onto the sun after it went completely dark. So I think that's what's happening there. It's tracking, but it just means I need a better algorithm for tracking it. And again, it's a time-based thing. So one of the things to do, as well as stepper motors, is to use a well-trained PID to actually track, to move this thing so it moves smoother and it's not going to have as much jitter in moving. So if we take a look at now, this is the data from the ambient light and the ultraviolet light sensor. You could see the ambient light is the blue trace. So you could see it's pegged, and then it drops down and comes back up. It's got a little bit of gnarliness here. I don't know if that's because of the tracking or just noise from the light. But I'm sure if I was to do some, low pass filtering of this data, I would get much smoother data. But the interesting thing to note here, if you just ignore this noise, this gnarliness noise, as I said, if I was to do this again, I could probably just use some kind of low pass filter here to get rid of that noise. But if you look, this is linear. This is the ultraviolet. The orange is the ultraviolet light. It's linear. It's pretty much linear here. It's a straight line. So ultraviolet would be a really good way to track the sun in the sky during an eclipse, because it got a nice linear path, and using a PID with that becomes much easier to go and travel. The reason I think this gets pegged up here, see it's like a flat line at both sides, is because I think this sensor here is just getting saturated. There's so much light coming off of the sun that the sensor can't handle it. It's too much light, and it hits its limit. So this ambient light sensor is probably not a good sensor to measure, the sun with. It probably need a better sensor. Now, keep in mind, these sensors, I paid like a few dollars for these. This was not stuff I spent a lot of money on. The IR camera, I think I spent the most on it. I think it was about $40 $30-40 to get that. The rest of the sensors were, dollars to go and get. So the other thing was my thermal flux. So I looked at my thermal flux and I got some good data from the temperature. So I converted the temperature I converted the data to a temperature of that plate. Now at C1, you could see the temperature is, pretty close to 25 degrees Celsius. So that plate got nice and warm. And as the sun gets covered up, it drops right down to about 6 degrees. It goes from 25 degrees to 6 degrees. So the sun heats the plate up to, 25 degrees. So almost about the 20-degree difference. Now, the problem is, I realized this after the fact, is that I can't use this to measure the flux. Because at this point, the flux here should be 0, but it's not. So what it's measuring here is the ambient temperature of the air. So I need to have a sensor mounted maybe below the apparatus in the shade somewhere to just measure the ambient temperature. And so once I've got the ambient temperature, I subtract it from this data, then I get the true flux. So this data is meaningless. It's just measuring temperature of the plate, and it's to measure the flux, I have to subtract the temperature of the ambient air. So to do this again, I need to get an ambient air temperature. So one of the things, as I was driving home, I almost drove off of the road. I thought, hey, you know what? Is it possible that I could measure the apparent speed of the sun? Because I've got azimuth elevation data from the servos. I got the rate of change of azimuth and elevation. Can I calculate the speed of the sun moving? Well, the apparent speed, the sun is not moving. It's the earth that's moving. So it's an apparent speed. Can I measure it? And the way you would properly do that is you'd have to pinpoint, get the XYZ of a point in space of the sun, one point, and then a moment later, get the same point at another point in time and calculate the distance, the vector distance between the two. And knowing the time, you could calculate the speed as a vector. Now, I couldn't do that because I didn't have any kind of reference point. I could probably jerry rig it because I could do something relative, but I didn't measure the where 0 was, and I couldn't. I felt it would be a lot more difficult to do it. So I thought, is it possible that I could take the azimuth speed vector and the elevation speed vector? So take the speed of the azimuth of the tracker moving up and down, and the speed of the tractor moving left to right, and they should be at right angles. Just take the vector addition of both of those and see what that is. Could I do that? So I thought I would try it, but first thing you have to figure out what is the sun's apparent speed at my location. So this varies based on location on the Earth, time of year. So I found this chart. This guy measured it at his location somewhere in the States. As he measured the time. And during different times of the year, he measured the speed of the sun, and he found it varies sinusoidally between 15 and about, just 13.75 or so. It varied so many degrees per hour, and that varies over time of a year. So in the summer, it's got one speed, in the winter, it's got different speed. So I thought, okay, you know what? Let me try and do a back of the envelope calculation. The Toronto sunrise on that day of the eclipse was 6:42. The sunset was 7:55. That means I got 853 minutes in that time frame that it was the sun was visible. And assume the sun moves 180 degrees in one day, which is about right for this time of year. It's about 180 degrees. So it moves 180 degrees, 853 minutes. it's about 12.7, 13 degrees per hour, which is not too far off this chart. So it's a reasonable number. So if I plot that data, this is the actual data of the servos moving, and I need to ignore the data on either side or in the eclipse, because we saw the servos kind of hunting around. So that data here is flawed. So if I discount that data and I just look from here back, you could see it's, it's not bad. It's around 13. At the start, it was kind of speeding up, as it's tracking, but it's not too bad. So I don't think this is an accurate way of measuring it, but I got data that's not too far off. So it was kind of interesting to see that the data wasn't too far off. So if I was ever to do this again, calibrate the position of your tracker so it knows where the horizon is and where, the sun comes up. So that way I could track the position of the sun. So now let me take you through the images. So the camera took over 3,700 images, and all I did was I dumped it into a film strip so it plays out as a video. And so here you could see the image. Now, one of the things I was disappointed in was how terrible this came out. Because look, at some points you're almost seeing a circuit board. And I couldn't understand what the hell's going on, but you could see it's tracking the sun. The sun's in the middle. And this is just, it's sped up. It's speeding up. So as we get closer to the eclipse, you'll see we're getting close to the eclipse here. And you'll notice something here. You see it's getting dim, 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 dim right there. Look, see how it's bouncing around? That's the tracker trying to lock on. It's losing the signal, and we saw that data bouncing around. Here it's coming back, and look, it's bouncing around. The camera is, the platform is moving around, and it's trying to acquire the sun. So I was kind of disappointed in this data, but hey, what do you expect for like a $10 ESP32 module with a little cheap little camera, right? But so it gave me good data, and that's just what it looked like. So I thought, okay, well, what the hell's going on? If I look at both my ESP Cam 32, which was in my taking pictures of the pinhole camera, which I'll show that in a second, and the picture quality was much, much better. And I compared it to my W Rover module. The only difference was this was using XGA resolution, and this is using UXGA. So the only thing I could figure out is maybe UXGA it's not a good resolution to use. Maybe I should have gone back and used SVGA or XVGA or VGA, and maybe I would have gotten better pictures. So also too, everything else in the camera was identical. That was the only change. That's the reason why I was showing you that. The only change was just the resolution. So I think it's I need to better check these camera resolution, because about a week, I got this all working a week before the eclipse, and in that week I was overcast. The sun wasn't out, so I couldn't really test it. It was raining a lot. The sun came out on the day that I was leaving, so I could go out and do some quick tests. But again, I couldn't go and change things, so I just didn't have enough time. I wish I had more time where I could properly test out the cameras to make sure they were working. So here's the image of the pinhole camera. Now, some of them, the pinholes, I'm not very good at making pinholes, but if you take a look at some of them, the ones that are which kind of roundish, if you look at those, you will see that they do get deformed. The camera took over 3,500 pictures, and again, I put it into a film strip. I put all 3,500 pictures in a movie, and I sped it up. So it only takes, to see the whole thing, it takes like 2 minutes, right? And as you go along, now you see it moving around like that. That's me moving the box. That's me moving the pinhole camera. So you see it's coming along. So it's like some of them are deformed. You ignore that. That's just me. But this hole here is circular. And as it goes along, you'll see it's getting deformed as we go along. And where's the eclipse? The full eclipse is around, geez, where's the eclipse? Should be around here. Oh yeah, right here. So here it's going into the eclipse now. It's going into C2 at this point. And you can see it's really getting distorted there. And so right here, it's in C2, it's total eclipse. Right? Here it's in C3, it's coming out, and you can see it's deformed. So it worked okay. But again, I wish I had more time to test this out. The problem is, how do you test an eclipse to see the deformation without having an eclipse? So that was one of my challenges. So one of the things I need to properly test the pinhole camera, but how? I could maybe make better pinholes, maybe check it to make sure I'm getting better images coming out. So that's it. That's all I have to say. I'd just like to leave you with this quote about Chuck Yeager. And this is Chuck Yeager. Chuck Yeager died in 2020. I don't know if you guys know who Chuck Yeager is. He's the guy that broke the speed of sound at Edwards Air Force Base. So part of the whole X series, flights using the X1 and X15 and stuff. And he, it's the quote says, you got to push yourself. You got to know your boundaries and push your boundaries. And that's the way you evolve. That's where you get smarter. And with me, I pushed myself here and I made mistakes, but boy, did I learn a lot by doing this. And this is how you learn. So I encourage people to push the boundaries, do a presentation about something you know absolutely nothing about, because you will learn in the process. So at that point, I will close this off and I will take questions.
Okay, Dave, that's really, really good. I'm quite impressed. You've done more in 4 months than I've done in 2 years. But that's very, very interesting. Okay, questions. Hassan, go ahead.
Yes, that was awesome, by the way. A couple of questions. The saturation that you saw, so it looks like the UV sensor didn't saturate, but the light sensors did. Any way around that? Like I would have, that was actually something I think about all the time watching the eclipse. Like, I'd love to see what sensor data would show. It should have been linear or somewhat linear because of the accounting for the circular shape of the moon.
But I think I'd like, okay, Hassan, finish before I jump in. Sorry.
Yeah, so I would have loved to have seen that plot. So what can you do to fix that? What do you think about that? How would you?
I think Hassan, the takeaway is, even when the sun is partially covered up, the amount of energy it's emitting is enormous. And so that sensor just didn't have the resolution to pick it up. So I think I needed to get a sensor that has a higher bound for ambient light. Like for UV, it was fine. It didn't saturate. It was able to, pick it up. But I think with the ambient light sensor, I don't think it had sufficient resolution to pick up that much energy coming off of it. And it's just a matter of price. As I said, I paid a few dollars for these sensors.
That's just me,
So,
Dave.
okay. So, and I don't know, I probably need a better sensor with better resolution. And I'm sure someone may have. Sorry?
Oh.
Yeah. So I think, that's part of the problem is using cheap sensors.
So on that note, do you think it was like, if you put sunglasses in front of it, you would artificially dim it? So the question is, was it where's the limitation? Was it the ADC, was it the sensor, or was it what?
Yeah, Hassan, I thought about that going into this, and as I said, I had a month to do this. I wish I had more time because I'd really like to take it out, put it in direct sunlight, and see what it was, and maybe by putting a filter in front of it, because a lot of cameras they have like those cameras, the ESP32. Most cameras you buy, they've got an IR filter, so
Right.
they filter out IR light, right? So. Um, I thought about doing that, like putting some kind of filter in front of it, but I just didn't have enough time. But I thought about all that stuff. I wish I had more time to go and put this together.
I think as Kevin said, what you want is dynamic range. One way might have been put 2 or 3 sensors with different levels of filtering on there, like sunglass
Yes,
type thing, and then you get like
yes,
the high. You got to pick your range though. You're gonna have limited range.
right, correct. Yeah, definitely, it's a dynamic range problem. It just the dynamic range is too low. So yeah, maybe by putting filtering it, you get a higher, well, not a wider, but your dynamic range shifts, right?
Yeah, and since you're a gamma ray guy, I'm curious about the UV sensor. Is it just that the UV sensor had more range, or was there just less UV coming off the sun?
I I don't know. I suspect there was less UV, and maybe the sensor is actually it's got like as Kevin said, it's got a bigger dynamic range
Okay,
for UV
and I really got to ask
because
this question because I just can't. I can hardly contain myself. Um, if you had a prism and you just spread the spectrum out, so you had a slit coming off the sun. I know this doesn't work for an eclipse, but just hear me out for a sec. You had a slit, you had a prism, you get the whole spectrum of the sun from UV to IR. Assume it's like a quartz prism. You could get infinite kind of all the frequency bands, could you not?
provided the crystal does not absorb energy at other sides of
Yes,
the
quartz.
doesn't use
Quartz.
filtering, right? Yes, theoretically, yes, you could, but you got to be careful of attenuation of those frequencies. And I'm assuming the diffraction pattern is linear. It continues to be linear as it goes out, right? And it
Okay.
should be.
Awesome. Thank you.
Okay. Okay, Kevin, you're up next. You had a question?
Oh no, I was just gonna say about the dynamic range. I mean, most sensors can't handle that, right? I mean, I had my SLR, and it certainly can't handle full sun to dark, and I even put a filter on it when it was getting close to C2 or whatever, and it was still saturating. I had it down to the smallest f-stop and stuff. So anyway, just comment. Yeah, that you're right. The $40 sensor or the $10 sensor or whatever is no way going to be able to handle it. So probably
It's,
graduated
it's a
sensor, graduated
$4
filtering, right? What?
it's a $4 sensor,
A
and
$4
the
sensor.
camera
Sorry. Well, look in your
is a
car on the dash. Look at the automatic headlight sensor on the dashboard of your car. Right? There's a little dome there, and it's like
yeah,
almost black, right? And that's what they use to sense that it's dark enough to turn your headlights on automatically.
yeah.
So, there's that. But and just the other thing about the your hammer effect on your servo for tracking and stuff, just balance it. Put an opposing weight on the opposite side.
I did that. I
Oh,
put in the
okay.
last. I put an opposing, but still, you've got a moment of inertia. You're
Yeah, and
moving
then
this huge
right.
plate, and especially if it's down, you've got a force now pulling it this way and a force pulling it that way. You've still got this huge moment of inertia.
Well,
And
that's a yeah.
use a
That's a
stepper motor.
power problem.
Yeah, use a stepper motor, because if you use a stepper motor, that problem goes away, right?
Yeah, as long as you don't exceed the holding torque. Yeah.
Yeah, well, if you use a screw, like the how they do it on the CNC and 3D printers, they
Yeah.
use a screw,
Yeah. The
right? And they're
reflected inertia
moving.
back through a ball screw is very, very low. So yeah, that
Yes,
helps a
yes.
lot. Anyway.
So
Okay. Sorry. Enough.
doing something like that would help, but that increases the engineering part of it, right?
Okay, Joe, you have a question for?
No, I mean, Hassan and Kevin both covered it in
Okay.
their question. So nothing else to add.
All right. Cherry, do you still have a question? You still there, Cherry? Okay, maybe we'll come back to him. Dave, I have two questions. The shield, if you will, that you had for the sensors. How did you determine that length? Did you play around with that, or
The thermal flux sensor, like my thermal flux sensor. It was a piece of metal I had kicking around.
Okay.
I just took it and I tin snipped. There was no science behind it. I figured I would just measure because it doesn't matter. It's arbitrary, the size, because you're doing it per square foot or per square meter or square millimeter. A flux is something per square area, right?
Right. And the other one is, how did you calculate the focal length number 1? I get why you did for number 2, but how did you do number 1?
Just measuring it, just taking holes and putting it in the sun and just measuring to see what it was, and saying, oh, that's the focal length, and then taking my camera and seeing how far it would focus on an object. And I see there were two completely different, vastly different. And again, it's a cheap camera, right?
Yeah. Well, you know what? for using a lot of the, as you call it, cheap, your words, not mine, components and stuff like that, you really got a wealth of information and a lot of mileage out of that project you did, Dave. My hat's off to you.
Yeah, and the interesting thing is the data is explainable. Like if you look at the RBN data, some of it we got, stuff going on and we're not sure what's going on, right? But with this, most of the data we got, we can explain what happened.
Which is pretty cool.
I can look at it, this is what happened. So it was explainable,
Yeah, so it'll only be Eric that'll keep you up at night and not your data. Okay.
Yeah.
Let's see. Anybody else have any other questions for Dave? Comments? Okay, well, thanks very much, Dave. That's most interesting. I can hardly wait to see what you come up with next.
And that's, by the way, Peter, so that and the beacon, they're both going to Dayton.
I thought
taking them
perfect
to Dayton.
That's great, Dave. Looking forward to it. Okay, speaking of Dayton, I know we're just running out of time here, but I wanted to talk. I've been talking to Hassan today mainly, and I think Hassan's going to try and put together the Dayton Transmitter Challenge. So one of the little conversations we had with Hassan was, does he have all the components on hand to build this project? So Hassan, were you able to get any further along with that parts list, or do you have everything? Do you need something?
No, I got home and the meeting just started, so didn't look in my junk box yet. So I'm sure I have the parts on my desk. I just have to find them. So that'll take weeks, but but I know how to do it. I've built it in the past. It might actually be. It's basically what we here. I'll sketch out the plan. What we got to do is build a Pierce oscillator. Actually, you want to stop the recording?
No.
Or you want to put this on YouTube for all and sundry to hear?
Just give the Cole's Notes version of what you're going to say.
Okay. All right. Okay. So the easiest way to do this is to use a hex inverter IC. So the inverter IC is you need a single inverter, and you hook it up in a feedback configuration. So the output of the inverter goes to the input of the inverter. And so that in itself will make an oscillator. For stability, they usually use 3 inverters. And so, you have the opposite. So that thing will oscillate by itself as fast as the circuitry can drive it. But you can put a crystal in the feedback path, and then now it's crystal controlled. So that will work. And I think you can probably get 30 milliamps or so out of it. Now, the thing is, if you want to get more power, easiest way to do it is just double up each inverter. or at least on the final output stage, make it put a bunch of inverters in parallel there, and now you will have an oscillator, and that should do the trick. That's the simplest thing you can build.
Yeah, it's a fairly simple outline on the rules and stuff. Like you can use either the 7400 series or the 4000 series chip, and then you can use any number of transformers, caps, resistors, whatever you want, right?
Mm-hmm.
You just only use one IC. So
That's right.
well, if you take a look at your parts, and if you need something, sooner the better, especially if somebody has to mail it to you. Dave, you got a comment? You're muted.
Yeah, Hassan, I've got tons of digital chips here. I got all kinds, because I used to build these transmitters for my rocket. I've got a bin full of somewhere here. Here. These are all beacons where they're using digital logic chips, and they at some point, and I got tons of them, and I got all kinds of. Here's one I have with the heat sink. You can see the heat sink on it there.
Yep.
Can you see the heat sink? Yeah. So I've got all kinds of chips which you could use. There's one there with a crystal. You can see, and that one actually works. It's a 14 megahertz crystal. I don't know if you can see it, right? But I had to put a PIC. I had to put a PIC chip to drive it to generate CW, right? But if you're just generating a carrier, you don't need that. But what you could do, Hassan, is take the actual driver. You're right. Take one of the drivers and connect that to the oscillator in a feedback loop to get it to oscillate. You take that signal and you feed it to all the remainder logic units in parallel. You put them all in parallel and you strap it, you feed that, and you'll get a higher current coming out. The other thing too, drive it past the maximum rated current, voltage. So most of these chips, I think they're rated to like 6 volts, 7 volts. Oh my God, run it at 8 volts. And all of a sudden you'll get tremendous power coming up, but the chip's not going to last very long.
Okay, now
you're going to burn it.
Yes.
Now to that point, Hassan, what we were talking about this afternoon, I did touch base with Eric, and he's confident that he can find some more dry ice. So you're
Perfect.
dry ice. He says he could probably do it. So fingers crossed.
And you got to be careful. Hassan knows this. He knows this. So I'm preaching to the converted. You don't want to get it too cold, because if you get that chip outside of its operating range, it may not operate as well. So you got to be careful if you're getting the chip too cold.
Right. Yeah, minus 30 should be fine. We take our microprocessors and take them down to minus 30 all the time in chambers. So dry ice will do the trick. Liquid nitrogen maybe is a bit difficult, but I've got a book here with a diagram. I'm going to pull it up. I'm going to show it to you guys in a second. So cooling is essential. I think going above 12. Does anybody know if it's 12 volts or what? Like, what's the power supply?
I'll tell you in a second. Their power supply, I think, is up to 24. Yes, a 0 to 24 variable power supply. Oh, you know what? I stand corrected. Remember, they are going to supply a 40 meter bandpass filter.
Okay. Give me 1 sec. I'm going to flip my camera around. Here we go.
Hassan,
Do you guys see this page here?
Hassan, I've got a whole bunch of Sprat articles where they build those transmitters. I've got a ton of articles. I don't mind. I could share them with you if you'd like.
Oh, please do. So, are you guys seeing my screen here?
Yes.
Yeah.
This is a classic book, one of my favorites, called the CMOS Cookbook by Don Lancaster. And they have a section here on crystal.
Oh, we lost Hassan.
Are you still? Can you hear me?
You did drop out, but we got you back.
Okay, so see this 10 mega ohm resistor? That's the key to the whole thing. So what you do is you put a 10 mega ohm from output to input. This is showing a NOR gate, but just assume it's an inverter, same deal. So you put that between output and input, and what that does is, excuse me, it biases it in the linear region. So it's normal logic is 0 or 5 volts, but this biases the input and output at 2.5 volts. So it's now acting like a linear circuit. And then you put your crystal here in the feedback path and it oscillates really nicely. And you feed the output to a second gate, and now you got a clean digital gate output as well. So the couple of questions: are we allowed to use digital? That's the first question. Like if you have a digital square wave output, it's obviously more power efficient, but the filter is going to take away all that. So it's a trade-off between it might actually work better that way, because let's say we use 12 volts or 20 volts and massive amounts of cooling. As long as we don't blow the chip, uh, we'll have a lot of output power, but the filter on the output, they supply the filter right before the voltmeter or the power meter, and that will filter out like more than half the power. So we got to do that experiment to see how we want to do this.
Well, it doesn't talk about what type of signal, whether you sine or square. It doesn't say anything about that.
Yeah,
but they're going to put a filter on the output. So
we could do the spice sim for this spice simulation, or we could just go ahead and build it. So there's two approaches. One is do the digital thing. The other approach is we just take a single stage thing like they showed. That'll give you a sine wave, and then just parallel a whole bunch of 6 gates, six transistors or 6 inverters. Put them in parallel, and they act like one inverter with a huge output current.
That's what I think you should do, is that, at least to start off. And if you have more time to play around with another circuit, then so be it.
Yeah, so we'll need a few parts.
You're basically down to about a dozen days.
Yeah, we can do it. The last circuit I built was probably an oscillator of this type. Okay. And I use it as a temperature sensor. They're so easy to use and so easy to understand. I love them. If we can get CMOS HC7400 series parts, those are the high current, I think. Those have a lot more output power. So if we can get some of those, that would be good.
That I don't have.
We can check Sayal. Sayal has the same stock of parts they had when I was a student. So they haven't sold them yet. They're still there.
Right.
DigiKey can have them to you tomorrow.
Okay. So we can look at DigiKey then, and then I can order a set of parts, not NOR gates, NOT gates. I don't know which one's better, but we can just order them in and see play around with them. And the larger parts are better, maybe with a metal can. So they have, or actually, Ken, you said that the plastic had better heat dissipation last time when you're talking about transistors.
I think that was Dave EAC that made mention, or somebody made mention of it. You're right. I can't remember who that was now. But there was the plastic did have a better dissipation than the metal can. You're right.
Yeah. The metal can had an air gap in the middle, but the plastic was continuous.
I think somebody had a question there. Was that you, Howard?
No, that was by mistake. I was clicking on the chat.
Okay.
Sorry.
So yeah, that's one avenue. The next question is, do they limit the input voltage, or can we just set it to anything we want?
0 to 24.
Oh, perfect. 24 it is then.
Yeah, they have a 0 to 24 volt variable power supply, a 40 meter bandpass filter, dummy load, and power meter. They'll be supplied.
Awesome. And so we'll get the dry ice from Eric. If he can get us liquid nitrogen, that might be better.
Build 2 circuits, one that's going to need the dry ice and one that does not need dry ice, just in case.
Well, yeah, the one that doesn't need dry ice is going to be 5 volts or maybe 10 at the most.
Yeah.
But
Whatever. Okay. Well, thanks for stepping up there, Hassan. That's great. It'll be it'll be good to put something down in there.
yep, get started on it.
Okay. Does anybody else have any other comments? Okay. We got about, well, we're approaching 9 o'clock, so we want to finish up at 9. So what we can do is a quick roundtable if we all do about 30 seconds worth. and that will take us to the end. So nothing much going on my bench. I did take a pause on the active probe. I'm now back ready to get back into that when we return back from Dayton. I discovered a few things that I overlooked, and that kind of made me take a pause and start doing a lot of reading and develop a board for studying the MOSFETs. Anyway, that's all that's been going on my bench. Hassan, or not Hassan, Al, you're up next on my list.
Oh, good afternoon. Good evening, everyone. Sorry, no camera today. Not much on the bench over the last couple of weeks. I did manage to finish that QRP Labs 10-watt power amp, and so it seems to work well. Now I got to put it into a case and some decisions to make. I'm not sure whether I'm going to turn this into a monobander or plug in low pass filters or what. So that's the next stage on that project. But life is getting in the way at the moment. So I'm not sure I'll be able to get this done over the next few weeks, but I'll give you an update. That's pretty much it. Not much else to report.
Okay, thanks, Al. And yeah, life does somehow get in the way of the hobby for some reason. Anyway, Dave, you been doing anything else other than your tracker stuff?
Nope. Yeah, doing rocket stuff, but you guys don't want to hear it. Just skip me.
Okay, next month. And yeah, Hassan, I saw your note there. Let's get together on the weekend. Sure, do some posting on Groups.io or whatever, and we can do a little meetup on the weekend and talk about your project. Okay, Drew, anything on your bench this month?
Well, I can't say on my bench, no. Remember, Rick was mentioning that his 3-element Mosley had broken down. The elements for 10 and 15 have coils in them, and the coil forms had snapped. So I spent the last 10 days making what I think is not a bad facsimile of the Mosley coil form. And so
oh, nice.
That was quite the experience, because making threads and getting this thing to work, very interesting. Learned a great deal about how to create threaded 3D forms. So that was that's what I've been doing.
Bring that out to breakfast. I'd like to see it.
Yeah. Well, I've printed them up 4. He says he doesn't want to go any farther than that, but I think they're as strong as the originals.
Yeah.
And it's just with PET-G. So the next step is to see whether he can put a coil on it.
Okay.
It's just aluminum ground wire, I think, is the coil. It's really, they're not very sophisticated.
All right, perfect.
Elegant in design, but not very sophisticated.
That's probably the best.
Yep.
All right, thanks, Drew. Hey, Frank,
Okay.
on your bench this month?
No, the bench has been gradually filling up again with bits and pieces that I have dug out and tested around the house. So we're getting prepared for the Central Ontario Hemfest as June the 2nd, a Sunday, and it's being held at the Kitchener-Waterloo Regional Police, let me see, their recreation center,
Okay.
just west of Kitchener. So I've got tons of stuff for anybody who's going down to Dayton to drop off and spend their money before they spend it at Dayton.
And Dave, you had a question there?
Yeah, exactly what Dave and Eric were planning on going by. I'll have the coffee or tea ready.
Over to you, Dave.
Yeah, Frank, that's I was going to say, we're going to be driving down on Tuesday. I think it's the 14th. It's the so we'll be driving down Tuesday, and we're planning to be at your location in the morning. So we'll be leaving my house 8, 9 o'clock in the morning, and I think you're about 2 hours from me, 2.5 hours. So we should be at your place by noon.
Okay, we got you down here, 14th around noon.
Okay, it's in.
Yeah. So
You better.
if you could do me a favor and just send me your address. I
Yep.
don't know if you got my email.
I did not get your email.
Yeah, it's DRAJNAUTH.
Oh, yours. Yeah, okay. I thought when you sent me one.
No. Just send me a message and put your address in
Yep.
and your phone number. So
Yep.
just in case anything happens, we can contact you.
Okay.
Looking forward to seeing you, my friend.
Okay. We'll be ready.
Okay, perfect. Thank you, Frank. Next on my list here is Kevin.
Well, not much to report here. Just hoping I'm going to get motivated more in a couple of weeks when we're at Hamvention. How's that? I might go spend some money though, so why not?
Yeah, exactly. I'm sure we can get you motivated in a couple of weeks. Okay, Kevin. Okay. Ken, anything on your bench these days?
Oh, nothing on the bench. But a couple of weeks ago, I have a friend who has an off-grid property up just north of Huntsville and west of Arrowhead Provincial Park. I went down with him and another friend of his, to install a solar system. Um, they did all the electronics. I built the frame for the solar panels. We installed eight, 250-watt panels, expandable to 16. What I was responsible for was the concrete footings were in place, and I had to use a drawing that they came up with and built all the solar panel framing for it. That took a good part of a day and a half, 12-hour days. Um, Unfortunately, I didn't have anything to take pictures with. I'm checking. My friend was doing some pictures, so I'm going to check with him. Um, I think it was Thursday we finished installing the charging system and tested everything with uh, a generator backup, and it works quite well. I'm very impressed.
Well, that kept you out of trouble for a weekend.
I think we were down on Tuesday, came back, Friday afternoon or something like that.
Okay, well, very good. Thank you, Ken. Joe, you're next on the list.
Yeah, I inherited 2 pieces of vintage equipment, an old Tech 2235 scope, 100 megahertz, and also inherited an old Heathkit IG102 RF generator. So I powered both of them up. The scope's fine. The generator, no smoke, but needs a little bit of work on it. So that'll be something. And I also got my hands on one of those nano VNA devices. So I did its first calibration with the 3 resistors that they give you, and there was something else. And I finally cracked a mystery with my I IC705 radio, because I was trying to use it for the whole Eclipse thing, and I wasn't getting anywhere with it. And then I finally discovered earlier this week that, being an idiot, there was a setting I didn't see, and that was allowing the USB to be an actual source to modulate. Right. So I finally turned it on, and then boom, I was getting whisper, no problem, coming off the radio, and it pretty well matched the performance of the 7200 that I ended up using during the eclipse. So
Okay.
then, with that mystery out of the way, I'll then putting all of the focus on that QRP build that I had. I don't have that working on the Era yet, at least not at the power level that it's at. So that'll be next.
Okay. Well, busy guy. Okay, thanks for that update there, Joe. Hassan, anything else on your bench? But I guess not. We're clear just for this challenge, I guess.
Yeah. Well, somebody, I met somebody who's building radios. I think I might have mentioned it. He offered to give a few units to test out. So if anybody, they're the sub 1 gigahertz radios. And so they're like long range, like 10 kilometers or something. So if anybody wants to put them through their paces and try them out, let me know, and I'll see if I can get you some.
Okay. All right. Do a posting on that one.
Sure.
Yeah, I think that'd be good. Okay. Thanks, Hassan. Interesting. Okay. A couple more here to go. We're at 9 now. So, okay, Cherry, anything on your bench? Yeah, Cherry's been missing in action there for a little bit. Maybe he's having computer troubles. Okay, Charlie, you're up next.
I've got a little mini production line going on my bench right now, trying to get 6 of my APRS units for measuring telemetry shipped off to the boys in the Yukon so they can get them up on some mountaintop repeaters. They're planning to deploy them in June, and so it's consuming a fair amount of my time trying to get them up and running right now.
Okay. Interesting to hear more about that when they get it up there, Charlie. Okay, thank you for that. And Howard, anything more on your T41?
No, I'm just working a bit on that. Almost finished the PA board, so I should be pretty close to testing or setting up the bias, and then I got to put it all together to test it.
When do you think? When do you think you'll actually get it on the air?
Well, that depends on how much smoke happens when I try it for the first time.
Okay, very good. Okay, does anybody else have any other comments, questions before we wrap things up?
Yeah, I do.
Yeah, go ahead, Ken.
Does anybody know of a new ham that needs a station? I've got an FT 450 with a power supply, mic, manual, and if somebody needs a station, I could mail it or they can pick it up.
Not offhand.
Okay, I don't. It's not worth selling, but if a new ham is looking for something, I just give it to them.
Yeah, maybe post it on the park group.
Yeah, I was thinking that too, but I was also worried about the certain people who say, "Yeah, I do," and then they turn out and put it up on Quark sales.
Oh, I see. Howard, you got a comment?
Yeah, I thought Rick or Y was friends with someone that just got their license. I can follow up with him.
Yeah, if you would, and let me know.
Okay.
Thank you.
Okay, good. All right. Any other comments? Okay. Well, thanks everybody for joining in tonight. Good crowd out. That's great. And like I said, see what you want to do for the 15th, and maybe what we'll do is, like I said, like we did last year, I think we checked in for the meeting from the 4 Days in May hotel, and maybe we'll do the same thing again and see who's around. Okay, well, good night, everybody, and we'll catch up with you later. 7-3.
All right, have a good
Dave,
night,
great
everybody.
job.
Yep.
Yeah, Hassan,
Yep. Thanks,
Hassan, I
Dave.
just sent the Sprat articles. It's
All right.
look at the SOAREX groups IO, and you'll see the SOAREX, the Sprat articles. There's 3 of them I found. There's probably more, but those are good ones in terms of showing you TTL transmitters.
Awesome. Thank you. I'll take a look at them now. All right.
Okay. Anyway, ciao.
Take care.
Thanks, Dave.
Oh.
Bye-bye.